managed to finish both the lab questions yesterday? No? Did the first one, but not. How many of you did the first one? Like, pretty much most of you. Second one? You did the second one? Yeah, that's fine. That's what I meant. Okay. And what about the homework reading yesterday? How many of you? Nobody did the reading. Okay. So then, okay. So what we shall do? Did everyone receive the email and you're able to access the documents? So I added one document there, which is a list of all the lab exercises. So let me maybe show you that. So you see this document here, which is called Labs and Homework. I just made a list of all. I made a list of all the labs and homeworks, and I'll add to them as we go. Okay, so your first two and today's are there already. So homework 1, did I actually mention? Yeah. So I'll put it there. So when you go home, at least you can look at it. Otherwise, you may forget what the reading is. Okay. So that should be your reference for what you do in the labs and as reading. Okay, since none of you have actually read the thing, so maybe I'll start with the definition of the Fourier transform. Yesterday, I just gave you some intuition as to why or how it was developed and so on. So today I will go slightly deeper, but I still won't explain all the mathematical sort of nitty-gritties. So there's obviously, for many of the things that I'm going to say today, there needs to be, the functions involved need to satisfy certain conditions. Right? So a mathematician listening to how I'm going to present this today will be horrified that I'm not going to state all these things, but I'm sure you can find that in textbooks. So I'm not going to really, and they're not actually relevant. I mean, we can assume those things work reasonably well for us. Without that, we won't be able to exploit this framework. Again, in future, yes, maybe some of these things are not, maybe they're too hard a constraint, and that means the Fourier transform is not that useful in certain contexts, and we'll see that as well later. For now, you don't need to worry about all those things. So yeah, yesterday just to summarize what I said yesterday was, that because the eigenfunction, because the exponential is an eigenfunction of the differential operator, it simplifies the solution of PDEs, right? Now, so let's go a little bit into detail and see how or why this is the case. Okay, so I'll start with what the Fourier transform does, right? So let's call this operator the Fourier operator. So if we have some function f of x, right? This is applies some transformation to this function f of x, right? And what happens when you apply this operator? Does anyone remember yesterday? So what happens when you apply the Fourier operator? Sorry, anyone? Lambda into f. Yeah, so that was if you had an exponential, right? So if you can represent f of x as a sum of exponentials, right? So let's say you could represent f of x equals sum of some coefficients and is that how we said it? Yeah, I can't remember what notation we used. Anyway, so if you can represent it like this, then when you apply the Fourier transform, which is a linear operator, it will apply to each of these terms, and each of these terms has an exponential, and we know the exponential is an eigenfunction, so it simply scales it by that value, right? So in the end, what you'll get is you will get back some function of a different variable, right? So it could be, I'll tell you what this variable is, and this function is the transformed f, right? So this is what I'm going to call the Okay, for now, let us assume that this function is over the real domain. So we can say, let's say f goes from real to a complex value, but for this example, let's just take a real function so that we can easily understand what this is, right? So which means now the transform is happening over the infinite 1D domain, right? And obviously, if you can have a Fourier transform, you can have an inverse, which means now if I apply the inverse of this to this, whatever is this Fourier transform function, the hope is that you get back the original function, right? This was sort of the requirement that we wanted of the transform. Okay, so now what this omega means is it gives you, so if you break down this complex exponential here, right? Yesterday we saw that if you put, lambda equals say 2 pi I, right? Which is what Fourier did and showed that this has very nice properties. Then what happens is you get something which is cosine 2 pi. So let's add something there. Some constant x it will turn out not to be a constant, but you get then I sine 2 pi omega x. Okay, so you get each exponential will become something like this. And what happens as a consequence is you get a sequence of cosines and sines. And because of this term appearing inside the sine and cosines, the natural name given to it was frequency, right? Because obviously in that case here, omega tells you how many oscillations this cosine will make, right? And if you increase this as the numbers increase, because that needs to be a basis, right? So we said it will have several lambdas there. So there'll be several lambda i's, which means now lambda I will get this. Maybe I shouldn't use I here. Let me use J. What happens now is we have different omega j variables, and they form different frequencies. So this cosine, you will get a number of cosines, right? So you will get a cosine like this, then you will get higher frequency cosine every time. So as you increase the omega, you get different numbers of oscillations for the same length, which means that somehow controls the frequency at which each of these basis functions oscillate. And for that reason, the natural name given to this is frequency, right? To this variable here. And what happens now is, so this side, this right-hand side is very often called, because of that, frequency, right? More specifically, it's the Fourier domain. Because obviously you can specify frequency with other bases than just cosines and sines, right? I can have, a basis that looks like this. There's no reason why I shouldn't have it, right? You can have bases that look like square waves. And that's what wavelets do. And that is also some way of characterizing frequency. So all of these methods are frequency domains. All of these methods give you frequency domains in which to look at a signal, in which case f of x. But this particular one we will call the Fourier domain. So very often, I think early on, people used to confuse these two, right? Because there was no other actively used frequency domain. But now, obviously, there are many. So we will call it Fourier domain. And so, as you can see from this, every function that satisfies whatever properties I said it needs to satisfy has a dual. This is also called its dual. So this function has a dual just by virtue of the Fourier transform. So this f of x, or maybe I won't write it here. Okay, that's the Fourier domain. This is often called the Primal Domain more generally, but specifically people may call it either time domain if you're working in this, or spatial domain if you're working with space. Okay, now, so the way people usually write this is like this. You might have seen this. right? Oops. From now on, I'm going to put hats on top of the functions so that it'd be easy to recognize the dual. Some people use uppercase and lowercase. I like the hat notation. Yeah, so this is a Fourier dual or a pair. Okay, so from now on, when I say Fourier transform of f, I mean f hat of omega. If I say Fourier dual, I mean there's f and there is its Fourier transform. Okay, any questions on this? Yeah. For what? Yeah. So that's what I said. If the function satisfies certain properties, and you can read that it needs to be square integrable, it needs to be finite and so on, then it will have its Fourier transform. What does this Fourier transform mean, right? So that's what I was going to say. So basically, the definition is just this, right? So f hat of omega there's the definition. So when I say Fourier transform, this is what that operator does. Right? So if you look here on top, this is an operator, right? This is an operator. And this is the definition of the operator. So typically, you could write, instead of doing this, what people do for definition in maths is they may write it as that, and then you're defining. So in this, I'm defining both. So there's 3 lines. So I'm defining this as well as this. So I'm saying this particular transform or operator applied on f of x, I'm going to call this, which I'm going to call this, which, so I'm defining this f here. So in one line there, I've defined both the operator as well as the notation. Okay, some people use this as well. This colon equal to, some people use. Okay, so so that's the transform. And now if you think about what's happening, you have some function, and this is seemingly arbitrary function appended to it, and then you're integrating this, right? It is not obviously arbitrary. We've seen why you need an exponential, and we've seen why you need this variable here. So what happens is, because your integration variable is x, the resulting function does not depend on x. X gets integrated up, and you're left with some function of omega. And depending on the function of x, or depending on the function f, you get a different, right? So that's the definition of the transform. So what was your question again? Yes, so for any function, you can actually integrate in this. So if this is integrable, then obviously this exists. Right? You can take any function, simply append it to this function, and then integrate it. So what you must realize is, obviously this is a complex integrand, right? By complex, I mean mathematically it's complex. That you have a real and an imaginary part, which means that the function f need not be real, right? It could be complex. So here, if you look here, the range, I defined it to be real. That's just so we can imagine these functions for today. But this can easily be a complex, and it's very often a complex function. And it doesn't matter, because the Fourier transform there, anyway, has something complex. So you remember, this is a function that has a complex range, right? So this could look at something like this, where a and b are functions, right? So you have some function of omega plus I some function, and we call that a. Which means, is everyone comfortable with complex numbers? Yeah. Okay. So which means this has a phase and obviously an amplitude, right? And we will look at it later, so I won't really go into this. And keep this in mind, because every time you imagine this operator being applied, you should imagine this being a complex value. Otherwise, it'll be very hard to explain further. Okay, so that, any questions so far? Okay, so yeah, question? No? Okay. So now what we'll do is we will look at, so actually there was someone who asked yesterday to show an example of how this helps simplify a PD, but he's not here. So maybe I'll postpone it till when he's here. Okay, but I can mention an interesting property which does this, right? So the Fourier transform of the derivative of a function turns out to be so if I apply a derivative on this function, it turns out that this, which was the original dual of L, now is just multiplied by omega. So you see, this is the key property which allows you to solve PDEs, which is that, and this is due to the exponential, which we talked about, right? So what this means is you can take an equation which has derivatives and convert it into an equation which is at omega times. And interestingly, this, even for higher derivatives, you just do this. So it works for higher derivatives. And this is one of the key properties that's used. Okay, so what this means is, obviously we can take any function, look at its Fourier transform, and look at the different frequencies. So maybe we can actually, Wikipedia has a very nice illustration of this. So if you look here, right, what this is saying, you see there's sinusoids here, right? And they're only showing the sinusoidal terms. If you have a particle oscillating in a circle, then its y-coordinate is the sinusoid, right? The x-coordinate is cosine, and the y is sine of the angle. So they're plotting the y-coordinate of that particle as it travels around the circle. And you can see if x is uniform, and you just trace that function of y, then you get something like a sinusoid here. And because theta is scaled by 1 here, you get something looking like this. Now, when it is scaled by 3, right, it oscillates much faster here. Okay. Now, here they're adding both. So they're adding these two, and they're showing you what it means. What it means is you have this superposition of both the circles. And the result is the y-coordinate now does this. Right? So by adding two consecutive terms in the series, you get a function from a sinusoid, you get to a function that's like this. And you can already start appreciating it looks like a square wave. Right? Now then you add another term and so on. And as you add these terms, again, you can just extend the idea, just superposing all of these things. Right? It gets obviously a bit complicated, but you can see that this starts approaching. You can start seeing that it appreciates. Yeah. So you can see that here, this starts looking more and more like a square wave. Similarly, here they've done this with different. So they've taken different frequencies here, and the scaling factors are different. And now when you superpose them, it starts looking like a triangle, right? So this tells us that if we take a suitable sequence, we can achieve these functions. And the Fourier series tells you, given a function like that, a square wave, tells you what these coefficients are and what the frequencies are. So how do you know which frequencies to choose here? So why is this 3, 5, 7, whereas this is 2, 3, 4? Does anyone know? Can you guess by now? You think about it a little bit. How would you get those frequencies? So this is what this also shows. Well, the idea is if we go back to our we go back here, right? What we've done is we've taken some function. This is why I chose to show a real function, because I can draw it now. So we have some function x, and we called it dual f of omega, right? Omega was this, and let's say I draw, right? What is the y-axis of this? Can someone tell me? So here I've labeled x, and this is f of x, the y-axis. Here I've labeled omega. What is the y-axis? F cap of omega, okay? So, can I draw f cap of omega? I just told you that f cap of omega, anytime I tell you apply the Fourier transform, I want you to imagine a complex function, okay? It is not a function I can draw, right? So this cannot be f cap of omega. It either needs to be amplitude of f cap of omega or its phase. Okay, this is something you should really build into yourself, and that it takes time. But anytime you see this function and we think of a Fourier transform, we should be thinking either amplitude or phase. Or if you can imagine a complex function, very well and good, you can do that. But don't try to imagine a real function, because that leads to all kinds of trouble. Okay, so yeah, so the amplitude of f of x might look something like that. There's something peculiar about real functions. Because we chose a real function, it has this property that on the negative omega and the positive omega, you have symmetry. Symmetry around the origin in this case, right? Anyway, I try to draw it as symmetrically as I could. Yeah, so your amplitude of f of omega might look like that, and your phase again might look something like this, for example, right? So you have your amplitude and you have okay, so what this omega is saying in this continuous case, because we looked at the Fourier transform, continuous domain, and so on, what it's saying is for different frequencies on this axis, it's telling you what the weight is. Or it's telling you, in other words, you can also plot A of omega and B of omega. That would have been fine too. Instead of amplitude and phase, we could have simply plotted A and B of omega, which is what we wrote up there, right? And now if you look at this, A of omega tells you, so remember the function was A of omega plus I B of omega, right? So this tells you all the cosine components, this tells you all the sine components. In the discrete case, instead of having omega as a continuous variable, this will be an integer. And for every integer, you know what to put in front of. So in this case, you have cosine 2 pi A of omega x plus I. So it's just this, sine 2 pi B of omega, right? And these coefficients here tell you what weights to give and what, so this here, this amplitude here tells you how to weight each component, and obviously you know what needs to go inside this. So if you look back at this, if you apply a Fourier transform to that, then you will identify all these weights, right? In this case, it's Fourier series because it's this. That's how you get all these things by simply applying the transform. Okay. So any questions so far? Yeah. Sorry? Here, you mean? Yeah. Sorry. So you have amplitude. So this is a bit more messy. So let's leave this out. I wasn't very rigorous. But yeah, they tell you at that frequency omega what the amplitude should be. So the omega, you're right. A of omega should be out, right? I wrote that in really messy form. So it should be more. Okay. Yeah, so they tell you what the amplitude should be at that frequency omega. And if you get zeros, so if this happens to be 0 at some point, that means you can skip that frequency, which is why in that Fourier series example, here 2 theta was skipped because the transform gives you 0 at 2. 4 was skipped because the transform gives you 0 there and so on. Whereas here at 2 theta it was not 0, and there's a component at every frequency. It depends on what your function. The triangle wave gave us this, whereas the other one gave us that. And the way people usually show this is by, some diagram like this, where each of these lines is a successive frequency, right? So theta, 2 theta, 3 theta, and so on. And it's telling you over time how it varies. And yeah, this visualization is also very nice, right? So it tells you this particular wave, it will show you its breakdown. It can be represented as a sum of sinusoids. Obviously, the sinusoids have been shifted both in phase as well as in frequency. And you can think of looking at each of these sinusoids, right? So these heights here are the amplitude contributions of each of the sinusoids, and they usually show it to you like this. If one of these bars is 0, then in that expansion, you won't have that particular frequency. In this case, I think there are zeros in the middle here, which is 2 theta, 4 theta, and so on, which is the square wave, which is why you don't see those. It would have been nice if they'd shown dots there to be explicit. But yeah, so I think this visualization, so this was what I was hoping as homework you would look at, and then today I could explain. But anyway, now you can go and read about it, and hopefully it makes sense. Any questions? So all this stuff is in 1D, right? And it extends to higher dimensions. Instead of this transform definition that we had here, we would have a double integral. We would have two spatial variables. This would be, f of x, y, and then you'd have one with x, similar term with y, and so on. I won't write it out. And this is very commonly used in images, right? In the analysis of images. So for example, let me see, just to give you some intuition, let me see if I can run this demo. Okay, here's an image. You can think of it as a function of x and y. At each point, there is some value. In this case, there's RGB. Pretend that it's one function. Let's say the average of RG and B. What we can do now is we can look at its past Fourier transform. Again, it turns out the Fourier transform looks like this. This is the magnitude. So this is omega x, this is omega y, and every pixel here in this image tells you for that omega x and omega y combination what the amplitude is. Remember those sinusoids or cosines or whatever, the height of that, which is what we showed as bars previously in 1D. Here they're showing it as brightness. So high brightness means the amplitude is high. If it's black, it means the amplitude is low. And you can, I don't know if you can see from there, but there are these dots. There are bright spots here, and there are some bright patches here, right? That corresponds to frequencies that you see, these are regular, right? If you think of a slice through Y, you can imagine that everywhere there is this white cement line. Yeah, that would help. Thank you. Yeah. Can you see better now? Thanks. So if you look at this Y slice, you can imagine that there is a spike at each of these, right? Low values, high value, low values, high value, and so on. And that shows up. These patterns show up, right? But why is one axis different from another, right? There are spikes on both. Why does this look different from this? Clearly the frequency here is different, right? So every regular period, there is this white line. Whereas here, you see some are long, some are short. So the nature of the signal itself is not isotropic. It's different in X and Y, so that's why you see a difference there. Okay, so what does this mean? This means that there's a lot of energy, because there's a lot of white here, in the lower components, low frequency components, which means sinusoids and cosinusoids that have a long period, oscillate slowly. Whereas there is not much energy in the higher frequencies, right? So this part, there's not much. And this part is very low. So one may want to ask the question, what would happen if I only kept this, right? It looks like, oops, it looks like I don't need anything outside this. So if I remove all of this stuff in the Fourier transform, now remember, this is f of x, this is f hat of omega. Now I've changed f hat of omega to g hat of omega, which means there is some dual of this, which is g of x. Right? The question is, what is that g of x? How can we get that? Maybe before I run it, I will just clarify. Right? So what we've done is we've taken f of x, which is our image, applied an FFT, looked at the amplitude. So we looked at the amplitude of f hat of omega. And then we were asking, okay, let's crop this, do some transformation, look at the amplitude of g hat of omega. Then we want to know what would g of x look like. So how can we go? We went from here to here by applying the Fourier operator. We went from here to here by applying some fancy crop operator. It's a nonlinear, some weird operator, but it was an image edit. And now the question is, how will we go from here to here? Yeah, so obviously we can apply an inverse Fourier transform. If we had applied an inverse Fourier transform on f hat, then it would have gone back to f. But because we changed f hat, it will go back to some other function, g. Right? So we can now look at what g would look like. So why are those numbers? So let's take this and ask what its inverse transform is. So there, that's what the inverse transform is. Right? And let's see if we can toggle back and forth. Okay, this was our f, and this is our g. It makes sense, right? We took some Fourier transform, we threw away all the high frequencies and said, give us only the low components. So we got some smooth figure. Actually, it's quite interesting. Despite throwing away a lot of the high frequencies, you can still see pretty reasonable lines, right? It's not that bad. So very early in image processing, people were excited by this because it meant that you can now compress your signal, right? You can take an image, apply its Fourier transform, and then throw away more than 80%, I think, in that image, there, the Fourier transform image. There, I think that's more than 90% of the pixels, right? It's gone, it's just black. So if I only know this bit, and I transmit that bit, I shouldn't say bit, that portion, over say a network or so, when the bandwidth was very low, at the time, people thought, oh, this is awesome, because now I can get back something that doesn't look great, but I probably can live with that. And obviously then people started asking, oh, how much should I remove so that these two are similar? And clearly we did something really stupid here, right? We didn't even think, we just took a circle. You can be more fancy about this. Maybe you can find a sparse representation for your frequency domain and so on. So there's a lot of work on this, and it's a very sort of old concept. People have used this for many years. Any questions? Yeah. Yes, of course. It's the same thing. Well, sound is exactly the same. I'm just showing you because somehow I feel with images it's very visual, right? And that's why I wanted to show it to you like this. Yeah, it's possible for any signal. In fact, it was all born. A lot of the theory was born with sound and radio waves and so on. But what's interesting here is for this g of x, we can provide a guarantee. What is the guarantee we can provide? No, we don't know if it has more energy, right? What we can guarantee is that the Fourier dual of this does not have any component higher than this, right? So now if we go back to our notes, so maybe I should put that notes thing on a different desktop so we can go easily back and forth. Yeah, good. Okay, so now what this tells us is because we cropped with the circle, the amplitude is the same everywhere, right? So that is square root of omega x squared plus omega y squared, right? If you call this omega now, because we are in 2D, what we're saying is the g of x, that signal g of x, does not have any energy above omega, right? This is also sometimes referred to as maximum frequency of g of x is omega. In other words, g of x is band limit. This is a common term in signal processing, right? What we're saying is this frequency spectrum is often called a band because you see bands of energy. And band limited tells you that there is a limit to where the energy can be for the Fourier transform of this function. So if you have a band limited function, anytime anybody says band limited function, this should pop up in your mind, right? And that's also one of the reasons I like to show this with an image, because you can clearly remember, oh, there was bricks, there were blurry bricks, that was band limited. The same thing happens with sound or any other signal. The minute you band limit it, it becomes smoother, right? And you lose detail, but for some applications that may be okay, and obviously it depends on what your band limit is. Now, why is this band limiting so relevant? By the way, we don't need to stick to just this, right? We could have done exactly the opposite here. Here, what we could have done instead, so let me close this because kind of got the idea. What we could also do is take the Fourier transform. Oops. So this may be a slightly different circle, but we can also clear the low frequency. Now it's not band limited because we can't provide any guarantees on what the max is. It is band limited in the sense that you know what the minimum frequency is. Right? But this is not what people call band limited usually. And yeah, now we can so you basically get all the edges. So you can immediately see that looks like an edge detector. Right? Perhaps you could just use this for edge detectors, and that's what edge detectors usually look like as well in the frequency domain. So the idea that now you have this dual space means you can do very interesting things. Right? It may not be new because people have been looking at this for a long time, but you can think of doing edits in this space instead of this space. It's less intuitive for certain things. Like if I want to move this brick here, I probably don't want to work here. It would be very, very difficult to achieve. But if I want to sort of get a global, and this is partially due to that integral we saw, right? Minus infinity to plus infinity. Anything you do is kind of global. So to do, if you touch one pixel here, if you want to move one brick here, it's hard to identify because every pixel here encodes every pixel here. It's an integral over the entire domain, right? So if you make an edit here, it affects every single pixel. It may affect some more than others, but it does affect every single pixel. Yeah, and obviously we can do, so it doesn't let me undo, which is annoying. But yeah, so you can also do things like this. Oh, no. Right, and you can choose what frequencies you want to see. So this tool is called ImageJ. You can download it over the internet, and it's quite fun to play with. It doesn't really require any installation. You just download, extract it, and it's a Java thing. ImageJ. You can see it is on this, right? So you see the toolbar title here. Yeah. So now you see you've applied some filter. This is what signal processing people call a filter, where you've removed low frequencies, you've removed high frequencies, and you've got this band. So you can think of your filter as stopping, you can think of it as a traffic policeman on the highway, stopping any vehicle that is smaller than a certain size and any vehicle larger than a certain size, right? And that filter which does this blocking is called a band pass. You're selecting which band to pass, and it's called a band pass filter. You remove just the center, people might call it a notch filter. They're different names, but essentially what they mean is by choosing which frequencies you want to suppress. And there's no reason this should be 0 here. I could add a Gaussian here. I could do anything I want, right, in this space, and I will have some corresponding dual. And some filters have survived time. So when people saw this, they were very excited. They started proposing all sorts of filters. Right? And some of them survived the test of time because they were actually useful, and others may be very hard to even find on the internet. Okay, so now we've looked at a lot of the terminologies that you would hear if you were in the signal processing area. So we heard band limited, you heard band pass, you heard filter, and so on. Hopefully you remember the connections, right? Yeah. Yes. Yeah. What do you mean if you want to integrate? Well, if you look at your signal as a 1D signal, if you linearize your signal, you can apply a 1D transform. No. Yeah. Because what will happen with linearization is it depends on how you linearize. Right? So the question is, let's take a simple example. I have a discrete space, say a 4x4 matrix. And the question is, can I make this instead of a 2D space, can I treat it as a 1D function, right? So yes, you can. You can look at this, of course, as consisting of 16, and this is what a lot of people do in computer vision. They look at images as vectors. Right? Any operator on the image is a matrix multiplied if it's linear. Yes, you can do this, but how are you going to do this? So normally what MATLAB does is it does some column major or row major. So if you do column major, then you would have something like this, right? So you would go, this would be 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Problem is these jumps from here to here. Once you make this jump from 4 to 5, what it looks like as a 1D function may be very different from what it looks like as a 2D function. That's the problem. So if you imagine, let's see, what example can we give? Yeah, so let's say we have a very smooth ramp. So let me create a hypothetical image, a 3x3 image, where the gray values here are 1, 2, 3, 100, 101, 102. right? If you look at this as a function like this, or yeah, you can even say 200, 201, 202. Now, if you look at this as an image, what you would see is there'd be very dark black, but slowly becoming white, not white, gray, slightly brighter gray becoming brighter, and then almost white getting whiter. As an image, it looks very smooth in this direction, but you can see all the discontinuities in this direction. Right? Whereas if you push this here now, this will look something like this. Right? So you have this jump up here, this. So the nature of what this 1D signal looks like will be very different. And obviously, if I now do a row major and I store these values, then it goes crazy, right? Because now I'll have 1, 100, 200. Now come back to 3 and go like this. So the nature of this, so it's not that you can't do it, but if you know something about your linearization operator, then maybe you can derive certain properties of this. So there's one more thing I wanted to say about this. Yeah, so what people normally do if they want to linearize is they use something like a Hilbert space traversal, right? Something like this, which gives you some nice properties there, and it avoids these jumps and so on. And yeah, so I think some people have tried looking at what happens if you have space filling curves, but I don't know what the state of the art is. Okay, so this was sort of the side. This is just so when you read it later, you'll at least know whether you can ignore it. Okay, any other questions? So that was okay. So now you know what band limited is, right? How are we doing on time? I was hoping we'd be here at 10:20, but a little bit behind. Okay, let's see how we do. Okay, so now let's do something interesting. So if you remember what we did with this band pass, right? We had some function f of x, and we looked at f hat of omega, and we cut it out, right? So this is the 1D version. So we said all frequencies below this will be 0, all frequencies will be above this will be 0. So we were left with something like this. Right? And then we went back here and we saw what the function looked like. That's what we've done. I've just drawn it in 1D before I explain what else I would like to do. Now, the question is, instead of blocking things here, what would happen if I block it here? So I take this, and on this side, if I block it off on this side. Now, this is F. So I will always draw sort of a primal on the left and frequency on the right. Okay, so that's my primal. How will this dual look? Any guesses? It's hard to imagine, right? I mean, unless you already know what happens to this specific operation, is very hard to imagine. So what I'm going to do now is what we have here. When I say block, what I'm trying to say is you have F, and you want to multiply it with some box. If I multiply it with the box is 0 here and 1 here. So if I multiply these two signals, let's call this G, then I get F times G, which is what this is. So what we're asking is, if we have two functions and we multiply them, what will happen to the Fourier transform? So what is a convolution? Yeah, but what is a convolution? Yeah, so we can think of, like if you have these two, yeah, so we already have the cheat answer. We will write it down here. We'll see what it means in a second. That's correct. but we'll see what actually happens to this, right? So let's see, what is the easy way to show this? Yeah, so if you think what we want is, we have f of x, so g of x, and what we're asking is, what is the Fourier transform of this? Now, the blind approach to doing this is you just write down the integral we know already. You write down f of x, g of x, right? We know this already. We've seen the definition. But we know that f of x can also be written as right? We know this. We apply the inverse Fourier transform on f cap. So we can, just for the sake of some algebraic manipulation, we can write f of x down as the inverse Fourier. Oh, I didn't write the definition of the inverse Fourier transform, but I'll write it now. Okay. So now what's happened is, I've simply written the definition of the inverse Fourier transform. It's almost identical to the other one, right? The only thing is we've swapped the integration variable because we want to integrate out omega, get some function of x. There's this minus missing here as a small detail. But that's the definition of the inverse Fourier transform. And we can manipulate these things. I don't know if I should show this. We're already behind. Right? So in the end, you will end up with, if we write down this, what we want is, right? That's what we want to find, h hat of omega. You will end up with something like this. So by simply manipulating algebraically, which I won't show you, you can go through the steps. So you can see how to simplify these things, rearrange the integrals and so on. You will end up with something like this. Okay. Now if you think about this function here, ultimately we want a function of omega. We got a function of omega because there's two variables here. There's omega prime. It's not the derivative. It's just a different omega. And there is omega. But the variable omega prime is integrated out. So in the end, you will get some function of omega, which is nice. At least it tallies at the basic level. Okay. And what this is saying is, you go, if that is omega, at each, so let's say you want to know what is h of omega here. Right? Sorry. Let's say this is omega, and you want to know where is h of omega. Then you take f of omega prime, where omega prime goes from negative infinity. So I will show omega prime in green. Okay? So omega prime, you go for all omega prime. It's continuous, but I'll just show it like that. You want to go from negative infinity here to infinity. And for all of those, you will take f of omega prime. So let's say this is f of omega prime at each of the omega prime locations. You'll take g of omega prime, maybe the star. That's the value, right? Remember again, f and g are both complex, right? Oh, actually I made a mistake there. That should be f hat. Obviously it's not defined for. This is the Fourier dual of f and the Fourier dual. And remember, they're both complex, so this cannot actually be shown like this. Let's assume that's the real value or the complex value of that. You have, this is g of omega prime. What it's saying is, you take f of omega, which is this, and you take g, but not of omega prime, but of omega minus omega prime. So let's say this is omega, right? So let's say this is omega minus omega prime. Because omega prime is negative, it's really far here, so omega minus omega prime will be somewhere here. It asks you to look at G there, then multiply these two values, right? Keep it somewhere. Now you take the next omega prime, multiply those two values, and keep adding all of that, right? It's an integral there. And when you integrate that, at the end, you will get some value here. Okay? That is h of. Seems a bit bizarre, right? I mean, we're integrating from here by multiplying f and g at totally different locations. But actually, it turns out there's a very neat interpretation to this. What it's telling you is, so I drew this in a very complicated way, intentionally, because that is how we would directly interpret it. But what it's trying to say is, now let's take a simple case where f hat is a Gaussian. So it looks something like this. And let's take g hat, for simplicity, to be simply a Dirac delta function. So it's a spike. It's a value only. It's actually a distribution, but let's assume we have a function which only spikes at 0. Now what will happen in that previous case? At any h of omega, what will be the at any omega, what will be the value of h of omega? You will take some omega prime, right? The value of the Gaussian there will be very small. And then you will take g at some other point, which is omega minus omega prime. You will get, it will be 0 everywhere else because, it will be 0 everywhere else. So you will end up getting 0. So as a result, the convolution will simply give you back. Any idea what it gives you back? Has anyone seen this before? So if my f hat is a omega is a Gaussian and g hat omega is just a spike, what will I get back as this? Spikes. Spike in the shape of a Gaussian. What does that mean? You will just get back a Gaussian. Okay? So this was also meant to be homework. I forgot to write it. So you can look it up and find out what the convolution should be. Try to do it step by step. Okay, anyway, so this process is called convolution. We already heard the answer, but that's what convolution is. So what we know now is if we have two functions, f of x, g of x, and we apply the Fourier transform, then we get f hat omega convolved with g hat omega. So rather than write this integral every time, we use the shorthand, the star or circle. People have different notation, right? So these two now form a dual, Fourier dual, f times g and f hat convolved with g hat. So that's a Fourier dual. And this is called the convolution theorem, what we sort of derived. And it has very nice properties. So what we say is when there's a multiplication in the primal, there is a convolution in the dual, in the Fourier domain. So now if we go back to what we wanted to achieve, if we know f of x is a Gaussian and g of x is some box, which is what we wanted to apply, then the resulting spectrum will simply be the Fourier transform Gaussian convolved with the Fourier transform box. So there's a nice sort of algebra now that comes out of this, right? So if you know the individual Fourier transforms, you can start working out what products would look like. Any questions? So was this completely new to anyone? No. Yeah, a few people. Okay, so that is good. But the reason I stress this is because we will keep talking about convolutions and so on. Okay, should we take a break now? Maybe? Yeah. Yeah, is it ready? Okay. Oh, I see. Okay, good. So I'm really behind. Okay, so we'll take a break. And 11:15. Okay, I think there's coffee outside if you want.